Hello everyone. In our last session, we talked about relative extrema and we talked about critical numbers. In this session, we are going to relate these two concepts and also do some examples in finding the absolute extrema of a function. So remember, when we talk of a relative extrema, what we're saying is that given a graph of any function, there are going to be some valleys or hills. If you're looking at a very small interval where the functions are, increasing or decreasing. So here, if you notice, like this little hill we have here, this is like a smooth little curve, and we can also draw some horizontal tangent lines over here. So this is kind of like a hill. And then we also have something scenario of a valley in a graph of the function. And these are relative because if you look at the bigger picture, the graph is increasing and decreasing without bounds. But in the small little intervals, what you notice is it has a relative maxima at 0 and 0 and a relative minima at 2 and -4. So that is a very important concept. And also we notice is the maxima which is happening, the value of the function nearby are all less than the value of the function at that point 0, 0. Similarly, notice this value which we say is a relative minima, all the values of the function near that little point actually are bigger or greater than the point at 2. Or the value of the function at 2. So this is one of the most important things when we talk about relative extrema. And from here, we started to talk about not only these smoother values, but you can have scenarios where you have sharper points, In this function, you have a sharp point here and a sharp point here. So these two sharp points are also like, the very steep peaks and steep valleys. And this leads us to the concept of critical numbers. What does a critical number say? A critical number is a function has to be defined at that point, and after that we look at two things: whether the differential of that function is 0, that means you have a horizontal tangent line, or whether the function is not differentiable at that point. That means you have a graph like this. In either scenarios, C is called the critical number of f, of this function f. And remember, we did some practice problems of finding these critical numbers, and I hope you guys have practiced some of them. And today, we are going to be combining these critical numbers with relative extrema in this theorem. The theorem says, if a function has a relative minima or maxima at a point, say x equals c, then c is a critical number of f. Remember, first your function has to have a relative minima or maxima, and the point where it has, then it is a critical number. It's like a one-way street. It says, if this is happening, then this happens. But if you would like to go backwards, if I say, oh, this is a critical number, then I do not know whether we're going to have a relative maxima or minima. Okay, so now we know we have learned theory. We are now going to find the guidelines to finding the extremas of the function, on a closed interval. Remember, we talked about the extreme value theorem. What is the extreme value theorem? So now we're going to work on that part now. Remember, the extreme value theorem says if the function is continuous on a closed interval a and b, then the function has a maxima and a minima on that interval. Now this is an important theorem. So now what we're going to do is, how would we like to find this extrema? In other words, we're going to try to find the extremes on a closed interval. In these scenarios, it is kind of using the extreme value theorem here only. So we would first of all find the critical numbers. we would evaluate the function at each of these critical numbers, then evaluate the function at each of the endpoints. Remember, in this one, you can have a maximum minima even at the ends. The least of those values is the minimum, the greatest is the maximum. Okay, so these 4 steps are needed. So now let's do a lot of examples now. So the first example, we would like to find the extrema of this function, which is a polynomial of 4th degree, 3x4 minus 4x cubed on an interval which is closed -1 to 2. Now remember, the first step is finding the critical numbers. That means you have to differentiate the function. So if my function is 3x4 minus 4x cubed, you take the differential, you get 12x cubed minus 12x squared. So the first step, guys, is find the critical numbers. So remember, I'm going to be using this as a short form, Cn. That means, now notice this is a nice little smoother curve, no sharp points or anything. So our critical numbers are just by putting the, and it is continuous and differentiable everywhere because it's a polynomial also. So we take this 12x cubed minus 12x squared to be 0. Take the 12x squared out, you're left with x minus 1. So what you notice is you have 2 critical numbers, 0 and -1. Now from the graph, we see this is a critical number and -1. And here we also see it's a kind of a little, valley. But nothing is, we see from the graph anything happening at 0. It's just like a kind of a little flat, you see. But to find the extrema of the function, what are we going to do? What is the scenario is we actually create a table. The first column would be the left-hand point, then the right-hand point. Remember, the left-hand point is what? X equals -1, x equals 0 are the critical numbers, and the right-hand point is x equals 2. Now we will evaluate these functions at -1, at 0, at 1, and at 2. So what we find is, at -1 it is 7, 0 it is 0, 1 it is -1. We are evaluating the value of the function, okay? At 2 is 16. So this is the minimum value, and f of 2 is the maximum. So let's look at the graph we have here. So the maximum at 2, which is the endpoint, and the minimum is in the middle, somewhere in the middle. Okay. Notice that the critical number x equal to 0 does not give a relative minima or maxima. And remember what we just talked about, that if you have a relative maxima, minima, the points where you have them, it is a critical number. But if I find the critical numbers, not every one of them can be a relative maxima or minima. And this is a classic example. Now, these critical numbers, as I said, need not produce the relative extrema. So that's one example. Now let's start with another example. Now here we have a rational function. We would like to find the extrema of this function, x squared over x squared plus 3 on the interval -1 to 1. Now notice this function also is an isofunction because there are no problems. It's a square function. No matter what you throw, this function will always be defined. And we're looking at the closed interval -1 to 1. It's happy over there too. Okay. And remember, when we deal with these intervals, we're always looking at real numbers. Okay. No complex numbers, please. So the first thing we're going to do is find the critical numbers. So f prime of x. And when you do the differential, I hope you remember the quotient rule. That's what we're doing. X squared plus 3 the whole square. Take the differential of the first, which is what? 2x. And times x squared plus 3. Negative the numerator as it is, and differential of the denominator, which is 2x. So what you're going to get is a 6x over x squared plus 3 the whole 0. And if this is equal, on the right hand side equal to the left hand side, basically it means 6x is 0 or x is 0. Now here we have one critical number, and we also have to look at the left hand and the right hand points. So the maximum over here when you plug in is 1/4. f of minus 1, because remember the endpoints are minus 1 and 1. The right endpoint also is 1/4. At the minimum happens at 0. So we have done this problem. Let me show you a graph of this function also. Okay. So here's the graph of this function. Notice that at 0, 0 it is a minimum. And remember, it's a continuous function from minus 1 to 1. It is having the maximum at minus 1, at 1, and both of them are the same values. Okay. So you can also verify it with the help of the diagram, but remember, whenever problems are given, you have to apply theory and do it analytically. And definitely you can verify using, your calculators, and what I'm showing you is Desmos.com calculator. You can use this and it will make your life very, very simple. And these are all free online softwares. Okay. Now let's go ahead, look at the extrema of this function. It's a cube root of x, and we're looking at the interval minus 1 to 1. Okay, notice when you draw the function cube root of x, there's no problem. So if you remember, the cube root of x is going to kind of look like this. Okay, so it's a kind of continuous function, and here is kind of some, kind of a little, but in the interval minus 1 to 1. So say it's minus 1 to 1. So minus 1 is, minus 1 and 1, say 1 here. Okay. Now, to find the differential. So if we find the differential of this function, what we get is 1 over 3x to third. Okay. Now, to find there, definitely it is not equal to 0. Do you see that here? This is not possible. So that means that at x equal to 0, the function is, the function is not differentiable, or f prime of x is undefined. You can say that function is not differentiable. Either way is correct. Okay. So therefore, x equal to 0 is a critical number. Okay, this is a critical number. So let's see whether it's a maximum or minimum. Now, left-hand point, say remember minus 1, right-hand point 1. The value of the function at minus 1 is minus 1. And at 0 is 0, and right-hand point is 1. So clearly, this critical number, as you can also see from the graph, is not a minima or a maxima. The minimum happens at minus 1, and the maximum happens at 1. Okay, let's do another example. Now here, we would like to find the extrema of the function 3 square root of x minus 3. I think minus x, it should be, minus x. Otherwise, this is not going to work. On the interval 0 to 9. Okay, now when you look at this function, clearly this function, yes, it is nicer because x is 0. It cannot take any negative values. Otherwise, this function is nice. And so let's see how the graph looks like. Notice, so this is the graph of the 3 square root x minus minus x. And if you draw this graph, notice it starts at 0 because remember, I cannot take negative values, and it crosses the x-axis at 0 and at 9. But what is more important for us is the relative maxima is happening somewhere around 2. Okay, so we can use our theory to find out that value, and then the rest from there. Okay, So clearly we notice that at x equal to, when you take the differential of this function, you get 3 to square root x minus 1 equals 0. And at x equal to 0, we know that the function, the derivative of the function is not defined. That means function is not differentiable. Therefore, it is a critical number because function has to be defined. Okay, at 0 it is defined, but the derivative is not defined. So now we would like to solve for f prime of x equal to 0. And we get 3 over 2 square root x, or x is 9 over 4. Okay, now, so that's our critical number. So when you plug in the values, at 0 it is 0, and 9 fourths again 9 fourths, and f of 9 is 0. So we have two minimums and a maximum. Okay, you can have more than one, minimum. It says the function attains a maximum and minimum. It's not saying a minimum or a maximum according to the extreme value theorem. A function, if it is continuous on a closed interval, then it attains a maximum and a minimum. You can have, this is an example where you can have more than one minimum too. Okay. Now let's look at a trigonometric function. Now, we would like to find the extrema of this trigonometric function, tangent pi x over 8 on this interval 0 to 2. Now, once again, let's look at the graph of this function, tangent pi x over 8. Okay, notice we're looking at extrema of the function, tangent pi x over 8 from the interval 0 to 2. Okay. Now clearly, these 2 points, if you notice, this curve from 0 till 2, notice what's going here. This one, you do not see any valleys or hills. So that means you're not going to see any critical numbers. Okay. So let's see what the theory says too. And so that means you're going to have a minimum and a maximum at 2 and a minimum at 0. And this graph totally shows no valleys or hills. So let's see what our graph, analytical thing shows. So when you take the differential, what do you notice? It's a secant square pi x over 8 times the differential of pi x over 8, that's pi over 8. Now remember, we're applying the chain rule, guys. Now, we know according to us, trigonometry, that secant function, there is no value such that secant square pi x over 8 is equal to 0. Remember, pi cannot be 0. The secant function is never touching the x-axis, if you remember that, in this interval 0 to 2. So there is no critical number. So what I'm going to do is I am actually going to show you the graph of the secant function so that you will see why secant square function there is no x value. Notice, this is the secant square function. From 0 to 2, notice it is not at all touching the graph. Rather, a secant function never touches the graph, guys. So that's very important to remember. This is your pre-calculus. That's where you learned about the graphs of the cosines and the sines and the secants and tangents. Okay. Now, let's come back here. So we see that we have an example where there is no critical number and the endpoints, the left-hand point, which is 0, is the minimum and the maximum is at the right-hand point. And we also saw it from the graph too. So, the usual thing, guys, we will now practice what we have learned. So these are called find the absolute extrema on the closed interval for the following. So basically just apply all the examples I've just done before, applies all of them to these problems. Definitely practice them. Thank you.